Everybody, welcome back from the break. Hope everybody's doing okay in the extended pandemic. So Sumeet Khatri is our next speaker. We're gonna have a number of students graduating from our PhD program next semester, and Sumeet is one of those. And this is a work that he did as a single author. So it's about quantum networks. Take it away.
All right, thanks a lot, Mark. And thanks everyone for being here. So what I'm going to talk about is this work that I have in quantum networks, and the arXiv number is also here in case you want to find out more of the details. So basically, ultimately what this work provides is a general mathematical framework for thinking about quantum network protocols and for constructing quantum network protocols. So let me start by talking about, in a general sense, what exactly is a quantum network. So abstractly, we can think of a quantum network as a graph. So the point here is that the vertices of the graph correspond to the sending and the receiving stations, and the edges of the graph correspond to entanglement links between those vertices. And in this particular case, the red lines that I've drawn here correspond to bipartite entanglement. So entanglement between two quantum systems, and the blue bubbles indicate multipartite entanglement. So entanglement between 3 or more systems. And we should think of these entanglement links as being the physical links. So these are links that are created explicitly through quantum channels that are connecting the nodes. And we should also think of the nodes as being spatially separated. So they might be separated by hundreds of kilometers. And the goal here is very similar to what we have in our usual sort of internet networking scenario, where we want to communicate, but not only now classical information, but in the quantum case, we want to communicate quantum information or execute some other quantum information processing task. All right. And many of these tasks involve entanglement as a resource. So it's one of the key things that you need in order to execute that task. For example, if you want to communicate, one way to do that is to first have a shared entangled state, and then you can do quantum teleportation. So because of that, the task that I consider in this work is entanglement distribution. Okay, so we have this network, and suppose that at some point in time, there is a request from two nodes that are not directly connected to each other. And that is the whole point here, which is that we want entanglement to be shared by two nodes that are not directly connected to each other. So it's like long distance entanglement that we want to create. So suppose that at some point in time, we have a request for entanglement. So suppose that the two yellow nodes want to share entanglement. And again, these are not directly connected to each other via a physical link. And similarly, we have two orange nodes here that at the same time make a request for entanglement. And again, these two nodes are not physically connected to each other. Okay. And what we want is for something to happen in this network such that the end result is this, where at the end of some protocol, the yellow nodes are entangled and so are the orange nodes. Okay, so what we want is to start from the request, which corresponds to some graph, call it G, and we want something to happen, which is the protocol, or sometimes people will call it a strategy, or we call it a policy in this work. What we want is some sequence of steps such that at the end, what we have is a graph that not only contains the physical links that were there originally, but also the so-called virtual links, which correspond to these entanglement links between nodes that are not physically connected. And we can think of that as corresponding to some new graph, call it G prime. So abstractly, we can think of a quantum network protocol as taking the original physical graph and corresponding and converting it or transforming it into a new graph, G prime, that contains the physical links, but also the virtual links. Okay. And so now there are many questions that we can ask here, right? So for example, how many pairs per unit time can we make? So what is the rate? How long does it take from the time that the entanglement is requested until the entanglement is achieved, right? And for practical purposes, we not only want to know these two quantities, which is the rate and the waiting time, but we also want to know what is the exact policy. So we have these devices that are communicating to each other, and what are the steps that need to be taken in order to achieve this goal of making long distance entanglement. So in order to answer these questions, we need to take into account the following challenges that arise in practice. So the first is that these physical links, they are often created probabilistically, because these, now as I will describe a little bit later, these links are created through loss channels, so, and using photons. And typically through these channels, the photons have some probability of becoming lost. And so because of that, the link creation itself will be probabilistic. What this means is that the graph is dynamic. So these physical links at any given time will not all be there all the time. So at some point we might have some of the links simply not present because the attempt to create those links did not succeed. And there's one other phenomenon, which is, in a sense, the uniquely quantum phenomenon, which is decoherence, which we don't necessarily see in the classical case. So decoherence of quantum systems is something that is essentially always there. And it corresponds here to the fact that the quantum memories that are holding these qubits of the quantum systems are imperfect. So there's noise, and this will result in reduction of the fidelity of the corresponding states. And typically for the applications that we care about, the fidelities need to be high enough so that we can execute the task that we want to. And particularly for this third reason, results from classical networking, which have been very extensively developed, don't always directly carry over into the quantum network scenario. Okay. So the task is to, in the presence of these practical challenges, come up with some protocol and answer these types of questions. For example, on the rate, the waiting time, and so on. So now, what does a general quantum network protocol look like? So a quantum network protocol can be broken up into stages, as shown here on the right-hand side in this table. In the first step, we want to create the elementary links. So the elementary links correspond to these the red lines or the blue bubbles, which are the physical links. We want to create those. And another step is to do entanglement distillation or some form of error correction in order to increase the fidelity of these links to some desired amount. Okay. Because typically these entanglement requests will also have some desired threshold for the fidelity. And then in order to actually create these long distance entanglements, we need some form of adjoining measurement or entanglement swapping. This would take two physical links, for example, and create one longer virtual link. Okay. And we also need some form of routing. So for example, if we want to create entanglement between these two orange nodes, there could be two pathways that we could take. One simple path is to go from here and then this way. So there are different paths that we can have in a network because it's a graph. And so we need to figure out which path is the best one to take. And all of these sequence of steps will happen over time, and we need some way to stitch these together. We need some way to coordinate these actions over time. And in this work, what I'm proposing is to do this type of stitching together using what's called a decision process. And a decision process, which I'll describe in more detail a little bit later, is related to concepts of rule sets or finite state machines and scheduling, which are things that arise also in the classical networking setting. All right. So essentially what I'm going to talk about can be summarized by this figure on the right-hand side. So the main thing that I do in my work is to cast this elementary link generation. So I focus only specifically right now on this first stage of creating elementary links. And what I do is I cast this process formally in the context of a quantum decision process. And what that means is what is shown here for one of the links, one of the elementary links. So we think about an agent corresponding to the nodes at the ends of the elementary link. And we think of the environment as a corresponding source that produces the entanglement between the two nodes. So it's some source of entanglement. And we do this for all of the elementary links, all of the physical links in the graph. Okay. So this is the first thing that I do. The second set of results corresponds to a particular kind of policy that we can think about, which is a memory cutoff policy. That's what I call. And this corresponds to the case where the quantum memories, which is what is true in practice, have finite coherence times. Okay. And the last thing that I look at is policy optimization. Right? And I'll describe all of these things in a bit of detail, although probably for the sake of time, I will not be able to go through everything in so much detail. And the first, and one of the things I will mention is the fact that I only talk about elementary links in this work, just as a first step to illustrate the concept. But it is something that is interesting to look at, which is how to generalize this to arbitrary or to incorporate these other processes like entanglement, distillation, swapping, and routing. So this is something that in principle you can do with this framework, and the idea is of this work is to show it for the elementary links and leave the remaining elements of this quantum network stack to future work. Okay, so before I get to the actual decision processes, let me describe how these elementary links are created in the first place. Okay, so as I mentioned before, if we zoom in on just one of these elementary links, what we have is a source of entanglement. And this source of entanglement will create some state, say a Bell state, and it will transmit them to the ends of this elementary link. Okay, so abstractly, we can describe the source as producing some quantum state rho s. This source state is transmitted to the nodes through some loss channel or through some other quantum channel, and which I denote by L. Now, once this quantum state has been transmitted, the nodes at the ends of the link have to perform, in general, some sort of heralding procedure due to the fact that the link creation is probabilistic. So if the source is creating an entangled state based on single photons, and we think of the channel as being a lost channel, as like, say, a fiber optic cable, then there will be some probability with which the photons won't arrive. And so because of this, in order for the entangled state to actually be useful, it has to be there. And so the two nodes that are at the ends of the link have to first confirm that the link was successful, that they both received their photons. And so that's what we mean by a heralding procedure. Okay. And again, we're going to take a very abstract picture and not physically describe what this heralding procedure looks like, but simply say that mathematically, it will correspond to some transformation of the output quantum states. So there are two possible outcomes for the heralding procedure. Either it succeeds or it fails. So these are the two outcomes that are described by two completely positive maps, M0 and M1, that transform the output state. Okay. So this process of the source producing the state, transmitting it to the end nodes, and the end nodes performing heralding, this process, we assume for now, occurs independently for all of the elementary links. So what I've described here by zooming in on just one of the elementary links would occur for all of these other ones that are in this graph. Okay. So now, based on whether the heralding procedure succeeded or failed, there are two possible quantum states that the end nodes will share. One of them is this rho 0 in the case that the heralding procedure succeeds, and there's this other one tau in case that it fails. And the probability that this heralding succeeds is given by the trace of the corresponding unnormalized state, rho 0 tilde. Okay. And the reason for putting this subscript 0 on the successful state has to do with the fact that once the heralding procedure succeeds, the end nodes will now keep these states in a quantum memory, okay, for use later on. And so the 0 signifies the fact that it has just, as soon as it succeeds, it is in the 0th time step in the quantum memories. Okay. So now, once the link has been created successfully, they're held in quantum memories, but these quantum memories, as I described before, are imperfect, which means that they will undergo some decoherence. And again, mathematically, the decoherence process can be described by a quantum channel. And this quantum channel will act independently on each of the qubits or quantum systems that comprise this link. So if we suppose that there are k quantum systems in that link, so in this diagram, k is just equal to 2, then at each time step that the link is held in memory, this quantum channel will be applied to the corresponding quantum state, such that after m time steps in the memory, we obtain this state. So it is just this channel n hat applied m times in sequence over time to the initial state. Okay. So this is the basic framework of this elementary link generation. And now I want to describe how we can think about this in the context of a quantum decision process in order to actually create a protocol. Okay. So let me now talk in general about quantum decision processes. And the definition that I present is essentially the one that can be found in this PRA paper from 2014. Essentially what we have, and this relates to the ideas in reinforcement learning. So this is where some of this nomenclature comes from. So we have an agent, and we think of the agent here as being the nodes in the network. But at each time step, the agent will submit some action to its environment, and the environment is described by a quantum state. And based on this action, the environment's quantum state will transition at one time step to some other quantum state at the next time step. And at the same time, the agent will receive two things. So the agent will receive some reward and also some observation. So I should mention that the observation, the reward, and the action are all classical things. The only thing that is quantum here is the environment. Okay. And this type of scenario, even though it's a little bit abstract, and even though the inputs and outputs of the agent are classical, this type of thing comes up in many different contexts. So we can think about things such as quantum games in the context of a decision process. We can think also of quantum control in the same way. And because this has been presented previously during this quote day, let me also mention that this type of thing can even device-independent protocols in quantum information can be thought of in the context of decision processes. And a nice reference for this is the PhD thesis of Rotem Arno Friedman. So this is just to give you some context about where quantum decision processes arise and what they are in general. But what I'll focus on in this talk is to think about this diagram on the right-hand side in the context of elementary links in a quantum network. Okay, so, right, and before I do that, let me just go into just a little bit more of the details. So, as I mentioned already, the agent here is classical, but the environment is a quantum system. And we want to know, based on the actions of the agent, how the quantum system of the environment will transition. And these are described by transition functions, which are, in this case, completely positive trace non-increasing maps. So x sub t is the observation of the agent at time t. Based on this, the agent will output some action, which is described by A, and this will lead to some observation at the next time step t plus 1. And there will be some map that will describe how the quantum system transforms. And I will describe this in detail a little bit later. Okay. And in this process, the goal of the agent is to figure out what sequence of actions to perform in order to maximize its expected total reward. So our figure of merit here is going to be this reward, right? So now in the context of networks, this is what we have. So the observations are just the link status, either 0 or 1. So whether the heralding procedure or whether the link is active at the tth time step or not. Okay. And the action of the agent, which are just the nodes of the network, is whether to keep the entanglement that is currently present in the links or to request a new entanglement link from the source. Okay, so again, the actions comprises two values, 0 or 1. Okay, and here I've described that. So we can associate random variables to these values. All right. And the next thing to talk about is the transition functions. So intuitively, we should think of the transition functions in the following way. So if the agent decides to request entanglement, then whatever entanglement is currently in the links should be discarded, and the heralding procedure followed by, the source transmission followed by heralding should be done again from scratch, right? And this will have two outcomes. So if the action is one, which is to request, then there are two possibilities, 0 or 1. So either the heralding procedure will succeed or it will fail. And the corresponding states that I described before will show up here. And the trace of the input state has to do with the fact that when you request, the state is discarded. The state that is currently there is discarded. Okay. And if the action is to wait, so in this case, the A is equal to 0, then as I described before, whatever is in the quantum memory will have a decoherence channel applied to it. And so that's what this signifies here. Okay. So these are the transition functions for our decision process. And I've already described what the agent and the environment are here. So now the remaining element is the reward. So now what we want in this particular case is for the fidelity of the quantum state to be as high as possible. So we will take that as our reward. Okay. So the reward function is going to be the following. So we assume that there is some horizon time, call it capital T. And this reward is given entirely at the end of this capital T time duration. So the reward here is conditioned on the link being active, which is what this chronic or delta is for. The reward is simply the fidelity of the quantum state of the environment, which is this thing here, which I will define precisely in a moment. The fidelity of this state with respect to some pure target state. So this could be the state psi would be, for example, a Bell state or some other multipartite entangled state, like a G8Z state or something like that. Okay. And the point is that this time horizon time, capital T, is given at the outset. So it could be that the agents are saying that I want my entanglement to be received after this amount of time. Can it be done, and what is the highest fidelity that I can get? So we should think of the horizon time T as being some time within which this entanglement should be created. Okay. And so that is the reward. Okay, and so now our goal is to maximize the expected value of this after capital T time steps. Okay. And we can think of this diagram on the right-hand side in the following way by explicitly writing down the sequence of steps in time. So the red boxes here, D1 and D2, correspond to the decision channels. So these are channels that would describe the decision that the agent takes at each time step. And the blue boxes here, E0, E1, E2, those would be the quantum channels for the environment, and they incorporate essentially the transition functions that I defined earlier. Okay. And so within the context of this diagram, we can think of the goal as being to find the correct sequence of quantum channels, in this case, just D1 and D2, such that the expected reward at the end of time step T equals 3 here is maximized. Okay, so that is the goal. And using this diagram and going through some of the calculations, we can write down explicitly what these states sigma hat 1, sigma hat 2, and sigma hat 3, what they look like. All right. I think I'm already kind of running short on time, so I will have to skip some of these explanations of these things. But the details are all in the paper. But the point is that we can write down all these states analytically. And this will be helpful when thinking about optimization of the policies. And so the conditional states for the reward that I wrote down earlier are given by this expression here at the bottom of the slide. Okay. So the gist of it is that this state has an analytic form that you can write down in this manner. Okay, so at any given time, based on the history, so this H superscript T is actually the history of the interaction between the agent and the environment. So conditioned on that history, either at time T, the link will be active, in which case the state is given by this, or at the T's time step, the value of the link is 0, which means that the link is not active, in which case it is just this erasure state corresponding to the heralding not being successful. Okay. And this M at T conditioned on the history is just the number of time steps at time T based on the history that the quantum state is held in the memory. Okay. So these are some of the results, which I think I'll just have to flash here. But essentially, the goal here is to find out what is the quantum state at any given time. And so that's what's shown here in these boxes. And these expressions hold for any policy that you have, because a policy here is arbitrary. And also it holds for any model of the quantum memories that you have. So any decoherence channel that you have. So essentially calculating the quantum state at the Tth time step for any elementary link corresponds to finding the probability that the link is active based on that policy and finding this joint probability distribution between the memory time and the link value. Okay. So these are some sets of results that are in the paper. And the main thing that we wanted to know about was the fidelity, right? So what is the expected fidelity after time T? Okay, so the first step is to define this function, which tells us after m's time steps in the memory, what is the fidelity of the quantum state? And it is just given by this simple expression here. Okay, and using this function, we've defined the following random variable, which is non-zero if and only if the link is active. So that's why this prefactor of x of t is here, because if xt is equal to 0, then the fidelity is also 0. Because the link is not active. Okay. So the point of this slide now is to show you that the expected reward after time t is simply given by the expectation value of this random variable. And we can write that down explicitly as shown here on the right-hand side as in terms of this classical quantum state of the decision process. Okay. And based on this, I will now present the results for optimizing the policy. Okay, so it is known in the classical case that the optimal policy can be obtained just by using backward recursion. So what this means is that you optimize for the optimal action at the very last time step and then proceed backwards in time and find each of the optimal actions at the previous time steps. And the same thing can be done in the quantum case, as I show in the paper, okay? And so I'm just going to flash up this result. So what we want to find is the maximum value of this expected reward. And the maximization is done over these decision channels that I talked about earlier, right? Because we want to maximize over all the possible actions that the agent can take. Okay? And this is basically a closed form optimization procedure, and it corresponds to backward recursion because each of these functions v, which if you're familiar with reinforcement learning, you can think of these functions v as being value functions. So we find the optimal value function at the very last time step, and then based on that, we can proceed backwards in time to find the optimal actions at the very first time step, and thus for the whole sequence. All right. And one of the other results here is the fact that using this procedure, we find that the optimal action here is always deterministic. So yeah, so in general, the optimal actions could be probabilistic, but we find that the optimal policy consists of actions that are always deterministic. So at any point in time, the agent can deterministically pick an action. It doesn't have to pick one with some probability. Okay. So that was kind of fast, I know, but I hope I gave some sense of what this talk is about. which is that the main thing was to illustrate the fact that any protocol in a quantum network can be thought of in this manner as shown in the right-hand side, where you have agents corresponding to the nodes and the environment is the corresponding quantum state of that link. And using this, what I'm proposing in this work is that you can use this framework to develop large-scale quantum network protocols. And this particular way of looking at network protocols from the context of decision processes is useful because of the fact that it leads to formulations in terms of reinforcement learning. Because reinforcement learning uses decision processes as its sort of mathematical backbone. So this would be one future direction in which to take this work, which is to actually apply reinforcement learning algorithms in this to discover protocols in a quantum network. Another thing to obviously do is to define these decision processes for higher levels of the stack, which would include entanglement distillation and joining measurements. Lastly, what I will describe is the fact that what I showed here is an algorithm for finding, a classical algorithm for finding the optimal policy, but it might be interesting to think about, and this is a line of work that people are already doing, which is to find quantum algorithms for solving these types of decision processes. And this would lead to quantum algorithms for solving, for discovering quantum network protocols. All right. So I think I'll end it there. And if there are questions now or even later, I'm happy to talk more about it. And of course, the paper is there. It's quite long and there are many details which I could not go through. So thanks.
Thank you, Sumeet. Okay, so we're a couple minutes over, but we might have time for like maybe one super quick question if anyone just had something they wanted to clarify. Otherwise, we'll get Victor's talk going here. So did anyone have anything for Sumeet?
Maybe a quick question. So you said something about the coherence because of bad memory. Did you take into account also decoherence because of photon loss or I don't know, like something like that, that you have entangled state, big entangled state, and you lose one qubit. So the rest is now not entangled state, it's a mixed state. Did you take it into account?
So yes, in principle, that is taken into account by the fact that there's some loss channel that connects the end nodes. So let's see. So there would be some loss channel that I just denote here by an L that would take into account in principle this type of thing. And this is also where the heralding would come in, because you would want to check to make sure that all of the nodes receive their respective photons. So if one of the photons was lost, then the whole thing would be considered a failure, for example.
Okay, thank you.
All right, thank you. All right, well, let's go ahead and stop recording and get Victor set up.